Okay, organic chemistry 2342. We're going to continue our discussion of carboxylic acid derivatives, and we're going to move on to some of their spectroscopic properties. So what we're going to look at now is we're going to look at the different fundamental groups and think about how it changes the spectroscopy. So if we start looking at just the carboxylic acid, the carbonyl functionality right here in the middle is going to be right in the middle centered around 1740 right here. Now, this is for a single molecule like diluted in solution. That's why we call it monomer. Occasionally they dimerize because they can hydrogen bond to each other. And so that can shift it down a little bit. But the other key thing to note is that it has this big peak down in the there we go. Big peak down in the 3000 range, where the OH peaks for alcohols would show up. That also shows up in the IR spectroscopy. So if we start as this is our middle group here, so we have our OH as our middle functionality right here, we can see that things like esters and hydrides and acid chlorides shift upfield to give us higher numbers. And then as we go to aldehydes, ketones, and amides, they shift downfield from there. And so let's take a look at that. If we want to think about it as the acid chloride here is going to be most shifted carbonyl upfield, you can think about it because it has a total of 3 different lone pair sets here. If we look at the anhydride, that's next on the list here, and it has 2 lone pairs, but it's giving electron density to 2 different carbonyls. So it's not shifting as much as it could. Then the esters are next. We have 2 lone pairs, and that shifts it a little bit less than having the regular carboxylic acid. And then the amides are shifted down below here because the nitrogen only has 1 lone pair to do it. And then once we make salts, it even shifts it further down here. So if you can think about it as number of lone pairs available to donate to this carbonyl group can shift it up into the higher regions or down into the lower regions. Okay, so what would a spectrum of that look like? So if we look at just the spectrum of propionic acid, the first thing we see is this big broad OH peak in this range right here, followed by the carbonyl peak, which is right here. Notice this is an ester, a carboxylic acid, so it's centered right at the 740 peak. Then we also have some in and out of plane stretches over here, but the 2 primary peaks are the big OH peak here and this carbonyl peak here. In fact, if we were to convert this to the acid chloride, we would see this peak shift up and this peak go away, and we'd only have our little peaks for our carbon-hydrogen stretch, and this big OH peak would go away completely. Okay, so now let's talk about the NMR a little bit right here. So for carboxylic acids, we have an interesting thing is the OH peak of the carboxylic acid is actually pretty high. It's above that of benzene. Remember, benzene's around between 6 and 8 ppm. And so that shifts it way high because it's an acidic hydrogen bondable proton. And if we have amides, again, we have an acidic proton that can hydrogen bond. So it's also shifted way up high, okay? Now, the hydrogen on an alpha carbonyl absorbs at like 2.5. So normally, if we just had an alkane like this, and then we have a carboxylic acid at the end here, these groups right here are going to be shifted, the 1.5 to 0.9 ppm. But the ones right here are going to be in the 2 to 2.5 range right here. So it's the ones that are just right next to that carbonyl that are shifted upfield, and then the rest of the alkyl chain drops down below. Okay, so let's look at the carbon NMR here. And what we see here is that the carbonyl right here is shifted way up high because of the double bond and the sp2 hybridized character of it. So if you have the carboxylic acid, it's around 170. Esters are similar, acid chlorides, amides, and nitriles are shifted much, much lower. Notice it's 117 instead of 170. Notice because we don't have 2 electronegative atoms bonded to that carbon here. We only have a single electronegative atom, and so that shifts us way down right here. So if we look at the carbons next to it, the carbon next to it is shifted up because of the electron withdrawing group here. And then after we've moved away one carbon, we've actually lowered it down to where it's close to where regular hydrocarbon spectra would show. Okay, so let's look at a proton NMR, what that would look like in the field. First of all, we see that this right here, this is a methyl group, but it's bonded directly to an oxygen. So it's going to be way up here in the 3.5 to 4 range. This is true for ethers as well as ester groups, the groups here. The other thing to note is that because there are no protons near here, it's going to show up as a single. There's nothing to split this peak. All right, the next peak of interest is going to be the one right next to it. And notice this is shifted above that of our normal alkane range, which would be here. And that is going to give us an idea that this is the one next to the carbonyl. And then our last peak is here. So if we look at our splitting peaks right here, this peak right here is split by the 2 equivalent hydrogens that are on the B carbon here. And this one is split by the 3 equivalent hydrogens on the A carbon here. So that's going to give us a total peaks of 4 because it's 3 splitting equivalents. And then this is 2 splitting equivalents is going to give us a total of 3. So we can tell that from our splitting alone, this has to be our isolated methyl group. This has to be the one that's next to 2 carbons, 2 hydrogens, and this one has to be the one next to 3 hydrogens. Okay. And that is all we have for spectroscopy on carboxylic acids.